Dear Heavenly Father, we thank you for this day again. I thank you for these students in this class and just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So today we are continuing our study of inner product spaces. And today I'm going to tell you guys about the concept of an adjoint. So we're going over the theory of adjoints. This construction is important towards building one of the major theorems in the course, namely the real spectral theorem, or just more generally this problem of diagonal. It answers, it gives some really nice results about diagonalization in the context of inner product spaces. That's somewhat of our goal. But anyway, so let's get started in here. So let me give a definition. Actually, where's my definition? I'm going to put the definition first and then we'll justify it, all right? If that's okay. Let V be an inner product space. What's wrong with me? I usually write. All right. And let T from V to V be a linear transformation. My hand's not working. Then we call the unique linear transformation T star that goes from V to V, for which the adjoint, let's say, come on, adjoint of T provided, I'm messing up my grammar's all over the place here, guys. I'm sorry. You'll forgive me. Or not, I guess. I mean, maybe I'll open up the course evaluations and it'll just be just a grammatical rebuke. Learn the English for all X and Y. I mean, I accept your criticism. All right. Anyway, the adjoint of T is called T star, and it is the unique linear transformation for which this equation holds. Now, I suppose the question then is, given the way I've presented it here, is wait a minute, does such a transformation exist, right? Yeah. And so the proposition is that follows. 5.3.2 says, yeah, suppose T is a linear transformation on V with, and, V is equal to the span of beta, where beta is orthonormal with respect to the, I don't think I've used this language yet, but this is a nice language. It's orthonormal with respect to the inner product which is given, right? So it's inner product orthonormal, and the number of things in beta is equal to n. All right, so I'm just taking my sweet time to tell you we have a finite dimensional vector space V with an orthonormal basis beta. All right. Then number one, T star exists, and guess what the matrix of T star is? Lo and behold, it is the Hermitian adjoint of the matrix of T. Right? Remember, we defined this before. That means the matrix of T conjugate, right? Transpose. The Hermitian adjoint, as we called it. And number two, the inner product of x with T of y is equal to T star of x with y for all x and y. Now that might look like, at first glance, like I'm not saying anything that wasn't already defined, but it's different, right? Notice here I'm moving T from the second slot to the first slot, and moving T from over here to over there puts a star on it. So like there's a very nice sort of clean calculational way to remember all these things is basically moving T from the first to the second adds a star, or moving T from the second to the first adds a star. Like we, yeah. So the question is, how do we prove any of this, right? Yep.
So are there T's where one of the propositions does hold and the other doesn't? Or one of the parts of the proposition does hold and the other doesn't?
Well, it is critical that the basis be orthonormal. If the basis is not orthonormal, then there's no guarantee that the matrix of the adjoint and the matrix of T are in any nice way related.
Okay.
So it must be an orthonormal basis. That's part of it. But I think that as to the existence of the adjoint, well, yes, it exists for a finite dimensional inner product space. Now the calculations to support that are essentially at the start of the section, so let's now return to those and try to understand them. All right. This is all for us finite dimensional, though. And I do think that is not a, I mean, I think you could study, I know you can study adjoint in infinite dimensions. I just don't have anything to say about that here at the moment, because we're going to focus finite dimensional here. So I'm not going to prove it directly. We'll find the proof as we go here, but let V be finite dimensional with orthonormal basis beta V1, V2 through Vn as usual. All right, and let T be a linear transformation on V. All right, then remember we found that the ijth component of the matrix of T with respect to the beta basis is what? We worked this out the other day, right? It was the inner product of T of Vj with Vi, against Vi. Because the jth column is determined by the action of T on Vj, and then we take the inner product with Vi to select the component, because we're working with an orthonormal basis, right? So it's just that. And so what I say next is I say, suppose we define S from V to V be the linear transformation with the matrix of S with respect to the beta basis, Hermitian adjointed, gives me T. I think equivalently you could say let, that is, assume the matrix of S with respect to the beta basis is simply the Hermitian adjoint of T. Remember that the Hermitian joint of the Hermitian adjoint is the thing again, right? The star star is back full circle. Now, I'm not super happy with this construction. Can you guys help me out? Like, how can we make this a little bit more concrete, right? Let's think about this. We got V. We've got V, right? I'm trying to define S, right? That goes from here to here. And I want that S to have the matrix. I want the matrix of S to be this. Right? So like, trying to think through it here, guys. So this is Fn, right? And over here is Fn. And of course I've got like the beta coordinate maps here and here, right? And, well, you know, I can define left multiplication by T beta beta star, right? And so I'm suggesting that we can construct S equals to what? Because you might wonder, like, I write this sentence, construct the linear transformation such that blah. How do you do that? Is the question I'm asking and answering at the moment. Here's how you do it. Just like this. Right? So the last shall be first. So we've got phi beta inverse composed of left multiplication by T beta beta Hermitian conjugate, and then composed with phi beta, I think should be okay. If I didn't mess anything up. So like I start here, I go down to Fn. Fn multiplied by the conjugate, the Hermitian adjoint to the matrix. That takes me over here, and then I do the inverse map to get back up. Yeah. Now, this is a linear transformation on Vy. Explain to me why that's a linear transformation. So the coordinate maps, are these linear transformations? We know they are, right? They're not just linear transformations, they're what? They're isomorphisms, right? So what are you looking at? Isomorphism, in the middle, left multiplication by a matrix. These are all linear maps. The composition of linear maps is linear, therefore, S so constructed is a linear transformation, all right? So, in fact, we can do this. It's not at all a jump, but there's the details of how to do that. Yeah. All right. Now, my next claim is that if you construct S like this, then the matrix of S, right, with respect to the beta basis is equal to what? How would you calculate the matrix of S? Do you guys remember? We do what? We do phi beta inverse of L of t beta beta star, right? Of phi beta of Vj, let's say. So what I have here, what I have in the parentheses is the jth column, right? That's the jth. Let me erase the big parentheses here and just say the jth column. Column J of that is what that means, right? We take the transformation, feed it the jth basis element, and then we have to calculate the coordinates. But what is this? We've got t beta beta star, right? What is phi beta of Vj equal to? First of all, what? Let me instead of. Oh, fine, I'll do it. All right, so this is Ej, right? But what does it mean to put brackets with the beta sub? What is that? What does that mean? That's just notation for phi beta, right? Of all this. Okay, of course these cancel, right? And what are you left with? The Hermitian adjoint of the matrix of T times Ej. What is that? Yeah, the jth column of T beta beta Hermitian adjoint, right? Therefore, the matrix of S, since this holds for an arbitrary column, the matrix of S is indeed, as we want it to be, the Hermitian adjoint of the matrix of T. All right? So this shows that definitely, so we've constructed a linear transformation, right? It definitely, S exists. Does S satisfy the criteria that defines the adjoint? By the way, the uniqueness of S, I would argue, is manifest from our construction. Okay, well, there is an issue. What if the construction depends on the basis, right? Like, what if you used a different basis? Would you still get the same S? I guess we could quibble over that, but I'm going to let that go for the moment. And of course, I would be saying, suppose you pick a different orthonormal basis, All right, let me go on here. So let's setting aside the issue of uniqueness for a second. Does S satisfy the condition we want? Does it, behave? Is it true that the inner product of, what am I supposed to have, t of x with y is equal to x with s of y? Isn't that what I want? For S to be the adjoint? Is that true for the S we've constructed? find out. So, all right, I guess I'll just suffer through the calculation. Let x be, well, let x and y be in V, right? Then, x is equal to the sum, I equals 1 to n, of the inner product of x with vi, and likewise y is the sum, I equals 1 to n, of the inner product of y with vi. I know this because we assume beta is orthonormal. So then, if we calculate the inner product of, I'm going to start with x and s. Well, golly. I don't know if I should start. Sorry, I guess I'll start on this side. I don't know which is the best side to start on, guys. Probably should just follow my notes if I was smarter, but that's not going to happen. Let's see here. So this, I'm going to pull the sum out already, right? So that's the sum I equals 1 to n of the inner product of x with vi, t of vi, right? Comma, the sum j equals 1 to n. This feels wrong. The inner product of y with vj, using the linearity of t in the first one there, So, all right. So I can pull out then. I think this is. I have my spider sense is tingling. In terms of this is not the right way to do this, but we are where we. Let's just let us see where this takes us. Now, that's not right as I've written it. You guys fix it. What did I do that's wrong? The inner product is sesquilinear, remember? It's 1.5 times linear. It's only conjugate linear in the second spot. So while it's fine to pull out the sum, it's not fine to pull out the scalar. When I pull the scalar from the second spot, I have to conjugate. All right? Okay, so what is this? Well, this right here, right, is that's t, beta beta what? T beta beta, which component? It's ji, right? Which is, by the way, equal to s beta, well, sorry, one step at a time here. That therefore is the transpose of it's the transpose of t beta beta, ji, right? ij, right? Which, if you want to throw in the conjugate in here, right? And a conjugate outside, this is the conjugate of the matrix of S, beta beta, because of course the matrix of S, beta beta by our construction is the matrix of T beta beta transpose conjugated, right? And by the way, it doesn't matter whether you conjugate transpose or transpose conjugate, like that commutes. So if I ever switch them up, if you're not, it won't hurt us. So then, so apparently, we have, so the thing, I think there's like a smarter way to do this calculation. I mean, because really, all of the fun stuff is happening on the basis, right? So I could have probably just proved this identity for the basis and then made a more elegant argument to just extend past the basis. But oh well, we did what we did. So this is and I still needed a ij component here, right? So the point is that this is then S of Vj inner product with Vi, right? Because that's how we calculate the ijth component with respect to the orthonormal basis for an operator. We evaluate on the jth column, and we take the ith component. So this is that. Now, what have I not added yet? It's important. This guy, right? Because that's here. So that's, what can we do though? We know the definition of the inner product allows us to flip-flop that, right? So what we have then is the sum I equals 1 to n of, we've got x with vi, the sum j equals 1 to n with the conjugate of y with vj. And then over here, we've got s, my bad, we've got vi, right, with s of vj. And now I just undo what I started with. Like, you see how I ripped out the x and the y into the components? I just undo this first step. Basically, this step right here, right? In reverse, and that gets me to bringing the x's back into the v's gives me x, and bringing the y components. You notice when I bring them into here, I unconjugate, or I conjugate, which brings us back to just the jth component of y, and that brings me to s of y. So basically, just by star in reverse. So there you go. X and y are arbitrary. This proves that given an orthonormal basis, we can construct an adjoint like this. I guess logically speaking, the question still remains: if we chose a different orthonormal basis, can we be certain that this adjoint wouldn't depend on that other choice of different basis? Any questions? All right. So let's see if I can show you an actual example here. And I'm just going to let the uniqueness question sit there for a while. All right. I'm not going to try to address that today, actually. The way the book defines adjoint is really different than what I just did. The book defines the adjoint in a very kind of sneaky, slippery way. The way I defined it is actually in such a way that we can calculate the adjoint without anything too slippery, right? Because to calculate the adjoint, you just need to find essentially the matrix, and then you can, we can write down a formula for the adjoint in terms of t, right? what is that formula? If we put this all together, like what's the formula? I mean, so like, we expect t of x, y to be equal to x t star of y, right? So this should be useful to define t star essentially. I suppose I haven't proved the other part of the proposition, have I? We should probably do that before I get to my example. So question. How to understand the inner product of x with t of y is equal to t star of x comma y. Let's see here. Well, if we let's start with xty maybe. That is equal to. I'm hopeful that the conjugate trick is going to work again for us here, right? Because that's equal to its own the double conjugate, yeah. And so that's actually the conjugate of t of y with x, right? By the axiom of the inner product. And now we can use the defining property of the adjoint to trade that t for a t star, right? Y with t star x. And then by the axiom again, we get t star of x with y. All right, so that wasn't bad. There you go. Which is what we were trying to show. All right. Let me take a break from regularly scheduled programming here and just make a comment about what this looks like in the real case, in the real world. So if we think about V being Rn with dot product, right? If we talk about left multiplication by A as their typical, mapping from Rn to Rn, we're asking the question like LA of x dot y is supposed to be equal to x dot L sub A star, whatever that is, right, of y. So how's that? What do you think that's going to be? Let's see here. So this is just AX transpose times y. And this is going to be equal to, x times whatever the matrix of this is. Let's call it B for the moment. X transpose times by. But sock shoes gives me x transpose A transpose y is equal to x transpose by. So lo and behold, my B is A transpose. In other words, the adjoint of left multiplication by A in the real case is simply left multiplication by A transpose, which corresponds to like the following identity of dot product, which you may or may not have ever noticed, which is AX dot Y is equal to X dot A transpose Y. So this is how this adjoint business plays out in the context of dot products. It just becomes transposition. So of course we got the complex conjugate flying around, so it's a little bit more exciting, but there's how it looks like in the real case. Oh man, goodness gracious. Jeez, look at that. Well, at least everyone's here today, right? Yes. They were good arguments, right? I think. All right. Sorry, this material, it takes me a minute to get up to speed on it. And I'm not sure what exactly it is. Partly it's like the way the book does things, it just weirds me out. And I will eventually be at peace with it, but until then I'm doing what I'm doing today, which I don't think is wrong. It's just, there's something elegant in the book I don't quite understand, is what I'm telling you guys. Oopsie. I think I'm erasing everything I need to do the problem. Uh-oh. Let's see here. All right, so example. I'm going to look at the differentiation operator on P2. That's a nice example. And this will give us a chance to take that Legendre polynomial basis we worked out the other day for a spin. All right, so example 1, which will be our only example, D from P2R to P2R. And we're going to do D of ax squared plus bx plus c is 2ax plus b, all right, the differentiation operator. And we're going to let the basis be the Legendre basis, which was 1 over root 2, root 3 over 2 times x, and square root of 5 over 8 times 3x squared minus 1. We worked out the other day we Gram-Schmidted this thing, and we found that it was orthonormal. This is orthonormal with respect to what? The inner product, we say, of f and g is integral from -1 to 1 of like f of x, g of x dx, right? So that was the inner product in question here. All right, so the next order of business is to calculate the matrix of D with respect to the beta basis, right? So let's do that. First of all, D of 1 over root 2 is what? The derivative of 1 over root 2 is? Oh, no. No. Thinking too hard. Yes. Let's try that again. The derivative of root 3 over 2 times x. Right, exactly. So that's just root 3 over 2, right? The derivative of square root of 5 over 8 times 3x squared minus 1 is equal to, let's see here, 6 times the square root of 5 over 8, right, times x. I guess that's it, yeah. All right, so to read off coordinates, if we can write the answer in terms of the basis, then we can read the coordinates off directly, right? Like this is what? This is the square root of 3 times 1 over root 2, right? And you guys help me fill in the blank here. Blank times root 3 over 2 x, right? I'm trying not to do too much stuff in my head. This is the square root of 30 over 8, right? Which is square root of 3 times 10 over 2 times 4. So I think I have the square root of 10 over 4 here, right? Although don't believe that. Don't believe that. Good night. What happens when you bring 6 inside the square root? I mean, I still got a square root of 6 out here, right? I only brought one square root. I only brought one of the 2 square root of 6s outside in. So I shouldn't have a 10 here. I should have a 60. I think. All right, so put this all together, right? And this shows me that the matrix of D with respect to the beta basis is equal to, all right, so the first column is 0. The second column is root 3 up here, and then zeros. The third column, it's got 0 constant terms, but the x term allegedly, that's a 15, right? 60 over 4. Is that 15? Okay. So I think this right here is the matrix of the differentiation operator with respect to the Legendre basis. Oh, man. Oh, phew. I was like, wait a minute. I've got something else in the notes, but no. Now I want to calculate what's the adjoint. The Hermitian adjoint of this matrix is just the transpose, right? So you got 0, 0, 0, root 3, 0, 0, 0, root 15, 0. And so then the adjoint of D, D star, acting on like, well, it depends on how you want to write the formula for it, but there was a star over here, come on. All right, so D star of, well, I guess I can write down the formula for ax squared plus bx plus c, but it'll take me a minute. So this is like a times d star of x squared. Oh, goodness gracious. Put me out of my suffering here. Oh, goodness. How did I write the answer in the notes? Oh, I had the good sense of, so like, this is a pain. Annoying. But if you instead write your input in terms of the basis, then it's not so bad. Right, so a times 1 over root 2 plus b times the square root of 3 over 2 x plus c times the square root of 5 over 8 times 3x squared minus 1. So if I write my input as it respects the basis, then I know what to do. See, because this means that I get, let's see here, I get, yeah, fine, a times the square root of 3 over, oh, good grief, a times the square root of 3 times the square root of 3 over 2 x, that's from the first column, and then plus b times the square root of 15, and Oh, well, yeah, it's just weirding me out. I wasn't expecting that. Okay, square root of 5 over 8. See, I keep I'm trying to judge the adjoint by it being the derivative, but it's not the derivative, it's a different transformation. So of course, when I try to like check my answer on the basis of the derivative, it doesn't make sense, because of course it shouldn't, because the adjoint of the derivative is not the derivative. It is a different transformation. But there it is. So the method of calculation I'm suggesting is not terribly profound. It's just find the matrix of the transformation, Hermitian adjoint it, and there you go. That put the thing back together. That's the formula for the adjoint. Now, if you're proving things about the adjoint, there's like other ways to go here, obviously, right? Like let's look at the next example. Hopefully the projector will work today. So you guys see, like, in order to write the formula for the adjoint in terms of ax squared plus bx plus c, like you have to like convert the I don't know, it would be a pain, because that ax squared plus bx plus c is not a natural formula in terms of the Legendre basis is all it is. So the next example, I'm looking at that inner product space we called H, which is the set of complex valued continuous functions from like 0, 2 to c, right? And this one here, what I did was I looked at a particular subspace of that infinite dimensional space spanned by e to the it, e to the 2it, e to the 3it, right? That gives me a subspace and three-dimensional subspace. And in fact, that's an orthonormal basis, all right? And then I defined a transformation by this. I said, feed it this, and that's what you get out, right? So that's my definition of the linear transformation. That being the definition, I can easily read off the matrix of the transformation as that. See? Like, for instance, this 1 and I, where's that coming from? First thing in the basis is e to the it, right? The output here, this is the e to the it output, right? And a and ib, where's that coming from? The first one and Oh, I'm an idiot. The A gives me here, right? And also where? There. So that's why I've got a 1 here and an I there. When I track B, that gives me this piece and that piece, which gives me an I up here and a 1 there. When I track C, C goes here and here. So I'm mapping to I e to the 2it and e to the 3it, which is why I've got the I and the 1 here. All right, great. And then I Hermitian adjoint that thing, right? And that just conjugate transpose, right? So you flip it over and put a minus on the i's. And then going back, this is the formula for the adjoint, just like that. So again, setting aside the question of uniqueness for the moment, all right? There you go, that would be the Hermitian adjoint in this case. Here's another example. I have a 2 by 2, matrix multiplication. TA is ma, where that's a given 2 by 2 matrix. I want to find T star such that T of AB is equal to A T star B. So this time, instead of doing the thing I just did, I just decided to try to look at the defining condition for the adjoint and just see by algebra what the formula has to be. That's more like what I did over there for my real comment. Yeah? So I need that TA inner product B is A T star B. But definition of the the Frobenius inner product here, I do TA with B transpose, which is MA B transpose. And over here, I have the trace of A with T star of B transpose. But to put the A here, I can use properties of the trace to move the A over here and move the M over there. Because of the cyclicity of the trace, M times this is the trace of this times M. And so once I've done that, well then I can see that this B transpose M must be the formula for T star B transpose, which then shows me that the adjoint of T here is just M transpose B. So I was able to calculate the adjoint without doing the very simple-minded thing I did in the last two examples, right? So which one should you do? Well, it depends on the example, right? I mean, we'd like to get conversant with both approaches. In fact, the way I did it in the first two times is kind of the weapon of last resort because it's very clunky working through the basis, right? It's kind of annoying. Whereas this is much more like, read it directly off with simple properties. But anyway, that's it for today, guys. So have a good weekend.